Hello, can you hear me? Hello,
Yes, sir.
screen visible?
Yes, sir.
Okay. Okay. I will continue with the quotient topology. So recall the definition. Suppose you have a map from X. I do not have topology yet here. Sorry, yes, sorry, I have topology here. I don't have topology here yet. Okay, right? It be a map. So here on this, y will give the topology sigma on y, b subset of y such that f inverse b belongs to tau. So then you check that sigma is a topology on y. Okay. Look, here f need not be onto. Though Willard has taken onto for this definition of the quotient topology, you don't need that. Willard has taken onto, but in another result he didn't take onto. That should be onto. He is using the proof. The proof. Okay, so this is the topology. 1, 2, sigma is the strongest topology on y such that f, this is continuous. That is, it's the meaning is what? That is, if f x tau suppose y, another topology, y alpha is continuous, then alpha is contained to sigma. Because if it is continuous, it will be here, and by definition, it will be in sigma. So this is the definition, you should understand. Okay. Now, what I did, and then actually sigma is denoted by tau f. And it's called the quotient topology. It's unique, of course. The quotient topology on y generated by both, actually. Generated by tau and f. Okay, fine. This is quotient topology. Now I have this theorem. This is important. Here we learned he should have taken. He is using the proof in that. This theorem 9.2 in Willard. Let me tell you. Page, if you're looking at page 60. Here the actual correct statement would be that, okay, let me write that. Let f x tau y sigma where continuous reaction. Reaction means onto. It's a French word. So reaction, injection, by reaction, these are French words. That means it is onto. This is he missed the statement. Okay. And if in addition if is either open, that means an open map is either open or closed, then then sigma is the quotient topology on Y. That is this is you need, because in the argument when you have B subset of Y, basically you need for this reason. F inverse B, when you're going back, in YAL this will be a subset of B. But if F is onto, then it will be equal if F is onto. That is why you need. This is the place. Okay. Now the question is, now the thing is, last time I told you something wrong actually, that I want to clarify. Look here in the example. Okay. The 9.3, the three-wheeler, page 16. Look, the example I have given last time. So here you are taking, look, x equal to 0 to pi. Last time I took 1, 0 to 1. That's why I multiplied by 2 pi. So here and y you take this unit circle. That means okay. So that here you give the map this. So all usual distance, because it is a subset of R. So usual, this is a subset of R square. So you take the relevant usual distance. Fx is in the ordered pair. You take a cos x sin x. Look, if you take 0, 1, then you need to multiply by 2 pi x, cos x, sin x. Okay. Now look here, this map. This is very important example. So f is continuous because each of these coordinate functions, these are continuous. Okay, component functions. F is continuous. And also onto. Because if you take any point on the circle, that can be written as like this, and so this will be this. Okay. Now the thing is that this is not open. Last time I made a mistake, and I think I'm not very sure what I said. This is not open. That I am going to tell you. This map is not, F is not open. But F is closed. Let me tell you how will I prove it. But if F is closed, and by this result, this is a quotient map, and this is the quotient space. That I was telling you last time. That unit circle is the quotient space, is a quotient space of this. Okay. So now F is not open, but F is closed. How will you prove that? Okay. F is Let's write it here. You should look at this point in the Willard. He has not talked about compactness, but if you use compactness, what I taught you last time, look, it's a closed bounded subset. So by Einberg theorem is compact. This is also compact. Both X and Y are compact. Now look, if you take a closed set, subset of X, suppose this is a closed. Of course, you can assume non-empty because empty set will give to empty set, which is closed. Closed X is compact, so this will tell you this is compact. This is continuous image of a compact set is compact, so that FA is compact since F is continuous, is compact in Y. But in a Hausdorff space, every compact set is closed. Here, everything is metric space. So this is closed. This is one way. If you know the idea of compactness, you can use that to prove that immediately. Okay. So this is closed. Or else, if you do not want to prove, I think Willard was using the Bolzano-Weierstrass theorem that every bounded sequence has a convergent subsequence. That can be extended to Rn also. So every bounded sequence here has a convergent subsequence. Similarly, every bounded sequence here also has a convergent subsequence. That you can use to prove that, but I do not think it. And you need the sequential characterization of closure points in a metric space. Okay, you can try that. That you can have it in exercise. But this is the way you can prove this is closed. If you know the idea of the compact, it is immediate. Basically, A is closed in X, so it is compact. Continuous image of a compact set is compact, but it is a metric space, so it is closed. Okay. Now, so this is a quotient point, but this is not open. Okay. How to show that this is not open? Well, I'm giving you an idea that, look, in the X, this is subspace topology, this is induced metric. So that 0 to pi, actually it will be easier in a sense to are not open. So you just to have an open set whose image is not open. Okay, since it's a negative answer. Look, is open in X. But what will be the image of this? In S1. Look here, this is 0, 1, minus 1, plus 1. So this will take this one. But this is open. So it will only take this one. Okay. Okay. There will be a break here. So if you want to show this is not open, look, you can check that. Actually, S1 will be open, any arc is open. Here I am having this point. So you can check that its complement. If it is open, it has complement, it has to be closed. Okay, complement has to be closed. But this point is taking here, but this point is not there. So you can do that. This is not open. Okay. Make sure you restart this example again. Okay, right? Fine. Okay. Now, what I told you that, okay, here I'm just an exercise on that. I'm leaving it on that. This is theorem here. Okay, let me write down that word. Suppose you have X tau Y sigma F. The quotient topology. Sigma is tau F. That is the quotient space. Okay. right? And F on 2. Now, suppose we have Z here. Z पे कुछ topology दो, alpha. Okay, right? So that suppose we have a map G. Sorry, y sigma G is here. H. G here, and this is H. Look, this you are coming. H is okay, right. Here, look what I'm saying. What is this saying that here you have a map. This is the full information you have from X star to Y sigma. Of course, this is the quotient topology. So particularly F is continuous also. Okay. Sigma equal to tau F. This is quotient topology. And here you have a map. You have third topological space Z alpha. Here you have a map G. Okay. So that look, the composition. Then you will come from here H, that is G dot F. He's saying that H is continuous, this composition. This is very useful result. If and only if G is continuous. Look, one way it is immediate because composition of two continuous maps is always continuous. So G is continuous implies this is immediate. Implies G dot F is continuous. So the actual importance of the result is here. If H is continuous, okay. Okay. H is continuous implies G is continuous. The ठीक है, you take an open set here. Let V be open in the look how I am using the going to use the idea of the quotient topology. V be open in Z, not Z alpha. That is V belongs to alpha. Now look, so I need to show that H inverse, need to show H inverse V belongs to tau. Okay, now look, H inverse V. Look here, you should know that here is the pre-image. This is not the map. Okay, H inverse, because H may not be one-to-one, onto bijection. So it may not, it is not as a map. When I say H inverse V means it's a pre-image or inverse image of V under H. So H inverse V is G dot F inverse V. This is also pre-image and it can be proved. It's the basic thing. This is F inverse G inverse V. This is always true for any composition you have that. Okay, these are all, don't confuse, these are not maps, these are all pre-images. So this G inverse V, F inverse V, pre-image. This is pre-image of V under G, and the whole thing is that it is a pre-image of G inverse V under F. Okay, now look, V is open in Z. Okay, I'll have to prove I have given H is continuous, so that H is continuous. This is H is continuous. I'm given hypothesis, so that this belongs to tau. But look how quotient topology was defined. Okay, look, V is here, so G inverse V belongs to the subset of remember that sigma tau F precisely subset of Y such that F inverse V belongs to tau. This is the idea. I'm using quotient topology. Now G inverse phi is a subset of Y, and F inverse in place of B you take this, and F inverse V belongs to this, so that G inverse V belongs to sigma tau F by the definition of quotient topology, and that exactly needed to prove that V is open in Z, and inverse V is open in belongs to sigma open in Y. So G is continuous. Okay. So look how we are using the idea of the quotient topology. Okay. This is an important result. This proof is very simple, but you should understand the proof, right? So that it will give you the better perception of quotient topology. Now, last time I talked about that if you have this quotient map, always we talk about basically on. So suppose that we have quotient space. Okay. Why this quotient topology? This is quotient topology. We will see now why usually we assume this is why. Now we'll understand. For the definition of quotient topology, I don't need it, but when I go for application and that good example, then I need the quotient came. Whether you talk about here quotient topology or quotient space, how we are justified to use the word quotient. Okay, right? That I told you last time, that what do we mean by the quotient? Like even in the algebra we did quotient group or a linear algebra, quotient space. Okay, something you divide basically. So that division is also here available. So this here I need to talk about decomposition space. I just look, this is not I'm going to test you in the exam and that, but you should understand these ideas. These are the beauties of topology, identification spaces. So what is decomposition space? This is first actually related to quotient space. So identification space basically is another name of decomposition space. Those here we let's say this is a special kind of this. It is not actually the same thing. Now look, so here I'm telling you the definition I'm taking there 9.5, but let me explain them. Suppose, yes. First of all, what do we mean by decomposition? Decomposition is nothing but partition. So suppose X, right now you don't need topology. So X, this is your X, and this you are partitioning. So basically an equivalence class is, remember that an equivalence relation on a set X and the relation on X is an equivalence relation if and only if it gives a partition. So this partition gives to decompose X into disjoint set. This is partition is same as decomposition. Okay. Now look, so each of them you can consider as a class. Now, so there will be identification comes through this relation. You give this equivalence relation, that will give you a partition. So identification. Now, each of them, here you have new space Y, such that each of them is a point in Y. So Y actually is talking about decomposition D, this D. Okay, right. So that, okay, let me notation and that. So that D is decomposition. That means X is union of F, where F is a subset of X, but F is actually a member of these, each of them, like this. F belongs to T. So this is the way you indicate a partition or decomposition. Decomposition and partition, they're same basically. Okay. So this is X. Okay. Right. This is X. And Y, on the other hand, Y I am taking this thing. Why is this? Whereas you can see that X will be the union of all these partitions. That means members points of Y is each of this class. On Y I want to give a topology. And which I will actually it will be a quotient topology. What topology I want to keep? Okay, first of all, how will I define? How will I define open set here? Look, there is only one way you can think of that. How will you do them? So, look here, Y, a subset of Y will be what? A collection of members of this. That means like this 2 you take, 3 you take, like this. A collection of members. But their union, suppose I pick up F1, F2 in T. Okay, so that F1, F2 is a subset of Y. Okay, but when I will declare it is to be open in Y. Well, if this is open, this is may not be open, may be open in X. If this is open in X, that means X star. Look, F1 union F2. Suppose this is F1, this is F2. This is union is a subset of X. So this may be open, may not be. If this is open, then declare this is open. If F1, F2 is open in X, declare F1, F2 open in Y. But of course, then you let's say this definition gives you a topology. Okay, right? So let me write down that. So it is very simple. You can prove it immediately that why it will be a topology. Not only that, it will be a quotient topology. So let me write it. Okay, what I'm saying that this is definition. Let X star be a topological space a decomposition. First of all, decomposition is nothing but a partition. It is a partition of X is a collection. Topologists, they usually prefer this word. Okay. Whereas algebraists, analysts, they prefer this word, partition. Okay. It's a collection of disjoint, pairwise disjoint subsets. Of course, the way I was giving you the picture, pairwise disjoint disjoint subsets of X whose union that exactly I wrote. Here it is very pairwise disjoint whose union is X. Now the topology how I am giving. Decomposition, the notation I have taken already, this D, script D, decomposition. Now, how do you give a topology? Now, so your new space is Y. Y is actually D. Y is actually D. Okay. Now look how is topology I'm giving. If a decomposition D is equipped or endowed, is equipped with the topology in which, be careful, this is a subset of D. D is my Y, F. So this is actually union will be some members of this. Okay. So here this is your X and these classes are members of D. So F will be union of some these partitions. So F subset of D, I will call it open. Let's say is open if a decomposition space is equipped with the topology. It is called open. Actually, it's called open. If I told you what will happen, I have union of this. Look, this. I have taken two there, F called F1, F2, just to illustrate the example. So this will be a subset of X. Is open in X. This I'm declaring. Okay. But you should check. This will give you a topology. Okay, this will give you a topology. I can call it, right now I call it the topology sigma. Okay, so that you are getting P sigma. You should check sigma is a topology. Well, I was talking about the quotient map and that. Okay, and this thing is called the decomposition space. Okay, so you should check this is a topology. In fact, you see that the theorem is now saying that I'm going to tell you that look, I'm giving this map X to D. What is this map? Okay, this is very simple. X, what will you take? Look, this is a partition. So you will take the class which contains X. X will belong to only one of them because it becomes partition. You take, you call it, I don't know, what will you call it? Px will be, Px is the, here you take, is the equivalence class rather, containing X. Or more precisely, I have not talked about equivalence class yet here, but that means is the set in D which contains X. Okay, is the point in X. Okay, so that this by the map this. Okay, let me tell you that. So basically, I can write this way. Don't sorry. Is the element of D containing X. Elements of D actually is some subsets of X which contains X. Only one of them will contain. And so this is well defined. Okay, this is well defined. And it can be shown with this. First you show this is a topology. Okay, now look, obviously this is on to the way I am defined. This is actually quotient topology. Okay, because you see this, I am giving you this thing. Which the topology is defined if you have this. Okay, so that thing is that this I am leaving it as he is a exercise. I am also leaving it, but this should be easy theorem. The topology, I'm writing that what sigma on a decomposition T of x is the quotient topology. Quotient topology is the quotient topology induced by, it is given by, generated by, induced by the quotient map. This is, you should check, it is induced by the natural map. Basically, quotient map I should not use, I will take natural map. Natural map means what I have given. P x to t. Okay, right. This you should prove. Okay. That means you have to show what? You have already have a topology here, xt. Here you have d sigma. You'll have to show basically, okay, here you have the p. You'll have to show that sigma is this. Well, look, you'll have to see how I define the topology. Exactly, this is the way I have defined the topology. Okay, look how I defined the topology there. Okay, this sigma. That is the same thing actually I was taking. Actually, I picked up the idea from here. That is the same thing. So you'll have to check that. So this will give you this will be a quotient topology. Here it is clear that if the classes quotient, because there quotient space, whether it is in group or in linear algebra, did it, that was giving me the classes. Same thing I have done here. So this is very natural. It is called quotient topology. But in Yan, when I took this in general, now look good. I said this is a quotient space and I gave the topology where sigma was tau wave. What will be the classes here? Here the classes will be this. Look how I'll do that. It is some mentioned somewhere here. Yes, F inverse Y. This is T. Look, since for different Y, this will be the disjoint pairwise. So this is your D. Okay, and you can check that. This you have taken this. Okay, let me write that so that this thing Y can be identified with T. Okay, so let me write what is the theorem. He is giving an exercise. I'm giving the stating the result. You should prove it, and then what we have already done, you can prove it. That what is the result? Let me tell you that. That's why it is called quotient space one. If look, if Y has the quotient topology induced by, you take this. This is onto. And on X you have the topology top. Then why is the idea of that? Then Y tau F is homeomorphic to the decomposition space here. This sigma I am taking that topology I have defined. We call it decomposition topology. Okay, right? Okay, decomposition is D, but you should understand what will be the decomposition space I'm talking. What will be the decomposition? Here this, where elements are these elements. I can write where I can write where T equal to okay. If Y is a quotient topology induced by this, then Y type is homeomorphic to the decomposition where D is this. But what will be the homeomorphism? I should tell you the homeomorphism. Okay, that he is saying under a homeomorphism, H Y tau F taking sigma, you have given that topology that we did. Tau F already have defined. Okay, yesterday. So what will be this? And the homeomorphism is such that homeomorphism, you should explain that such that if this is this, so such that H dot F is the natural map P. Okay. Already I have given you that result. I proved it. Basically that's simple. So that what is this? This is your X tau. Okay. This is Y tau F. This is, look, D. That topology you have taken. Sigma. Okay. Here it is coming the map F. Here is coming the map P. Okay. So here this H. That means H you can define. How will you define H? Okay. This is H. H dot F is coming. So you'll have to under a homeomorphism H such that so that you'll have to define H. How will you define H? Okay. Look, here is Y. Here. So define HY equal to, look, this is well defined. F inverse Y, it's a class. It's okay, it's a partition here, decomposition. So F inverse Y is the member here. So you define. Okay, so the map is well defined. Okay, and because of that, previous result I proved on that H will be continuous. Okay, and you can see that what will be H inverse also. Here H is a bijection. Prove that. Exercise. Prove. H is a homeomorphism. Look, I am giving it another name, but F inverse Y, that is the same thing is coming in that. Y is going to this, so you can prove H will be a bijection. Of course, H is onto. Okay, by this, because these are the class precisely. H is onto, and H will be a bijection because H Y look H y1 equal to hy2 मतलब क्या है? That means f inverse y1 equal to f inverse y2. That means they are going to that whatever element you take x, that fx will be same as y1 y2 and that. Sorry. So if that let me say. So define hy equal to f inverse y. Okay. Now don't forget this is decomposition, pairwise disjoint sets. So that obviously if you have any partition will be like that here this. So it is here. So this is obviously onto. This is clear. And 1 to 1. H y1 equal to h y2 implies f inverse y1 equal to f inverse y2. Okay. This is the thing. Wait a minute. Hy equal to f inverse y. Hy1 here you should understand that also. That what does it mean that? That hy wait a minute. y1 equal to y2. But what is the meaning of this? Look here, the way I have defined it is already assumed that here, if this actually this is cleared from the definition, this will be equal if and only if y1 equal to y2. That is actually the definition, that f inverse y1 f inverse y2 decomposition if and only if y1 equal to y2. So that's the way I'm taking the decomposition. This is equivalence relation. So this is actually part of the definition here, that f inverse y1 and f inverse y2 will be equal, the same class, if and only if y1 equal to y2, because y1 y2 are different. Okay, they will be different because that's from the follows from the function. Look what I am going to do that. Okay, let me see. Let me see that. If y1 not equal to y2, suppose, now x belongs to, suppose you take, this will mean fx equal to y1 and fx equal to y2. Then y1 will have to be equal to y2, otherwise it won't be a function. Look, fx is single element here. So since f is a function, y1 equal to has to be equal to y2. Because if y1 not equal to y2, then f won't be a function. So this is true. समझ गया? Basically, you need, since f is a function, means what? Single valued, not multi-valued function, since f is a function. Okay. So that H is a bijection. H is continuous by the previous result, you'll prove it. That H inverse, okay, that H inverse you'll have to look H inverse. How to show that it's continuous on that? Look, H, it's not like that they're in the what's just for, wait a minute. So H is a continuous, look, if Y induced by the X and that, Y has the quotient topology induced by that. So induced by this F already we know it is continuous. So that previous way you will prove that. Okay, that P. Now look, if H is continuous, you'll prove it. Okay, similar way you will prove that. That look, actually, if you go for this, suppose F is 1 to 1. I'm not doing that actually. So H will be, sorry, H will be actually P dot F inverse. So H inverse will be actually, when you take as pre-image in that, F dot P inverse. Okay, so this is the thing. That means, okay, look, H, basically you can say that H is an open map also. You can prove that. Or you can show that this is continuous. That will be the same thing. Okay, so I am leaving it to you that you should check that. If you can't do it, you can ask me. You can ask me Hers. You can ask Hers also. Okay, so this is just the idea I'm writing. These are not maths, but this tells you that when you plug here, something you plug here, then actually it will be like this. Okay, this makes sense because these are the pre-images, but actually it doesn't make sense unless there are one-to-one bijection and that. But this is the, you just use the idea that what will be the H inverse. Okay, that you always do. Okay, so that you will show that. Now the thing is, so that H, so H is a homeomorphism. Now you see that this is actual quotient space because I came through that. I did the partition and this is homeomorphic to that. So that basically this space can be identified with this. Okay, that's why it is called the quotient space, because this is actually geometrically, visually it's a quotient space. Okay, that's why it was called the quotient space. Here I explained all these things to give the justification why it's called a quotient space, and correspondingly it is called quotient topology. Identification space, I already told you that, same as decomposition space. So identification. Now, okay, let me finish that. Now you, with this result, okay, with this result I told you last time that, now look, here 0, just now I did, map I have given, unit circle. So that means if we have a quotient map, that will be a quotient space. This is onto, just I proved it. This is a quotient map because this is continuous, this is closed. Okay, so this is actually quotient space. But the thing is that geometrically, just now what I was talking about decomposition. Okay, look here, decomposition will be that, look what I am doing. For each point other than 0 and 2 pi, for each point is going to this. Only for at x equal to 0 and x equal to 2 pi, the same point. So that here the identification, what it is saying, that example 9.212, sorry, page 62. Everything I'm teaching from Wheeler. Okay, so here you are doing this actually. If you take identification space, okay, so you 0 and 2 pi you are identifying. That means you are taking it as a class, say, and other, if x doesn't belong here, x doesn't belong here, then x itself is the only class. That means if your x is this 0, 2 pi, look, that means what I am doing. This is 0, this is 2 pi. Every point I am leaving intact. Only 0 to pi, I am joining them. Okay, if you join them, then you get the circle. Okay, that means 0 and 2 pi now are identified. Both these 2 points are identified as one single entity, and others are left intact. This thing. So this is actually quotient space. Okay, right. This is identification space, same as decomposition space. Your decomposition is very simple. All the points you are leaving intact, only 0 and 2 pi you are doing it. So that way you are getting unit circle is a quotient space of this. Then you say, what is the advantage of this? The advantage of this is that often we study S1 in mathematics. Always happens that something little more complicated things you do not study directly. You study via something else. The quotient space has many properties coming from here, but this is much easier to handle. Okay, so many properties of S1 I can handle through this. That's why it is important. Now here, okay, so this is one. Next thing is that look here, you have this square. Okay, right. It is not exactly square, but you should not bother about this. 2 pi 0, 2 pi 2 pi, and 0 2 pi. Now look, if the arrow is in, if I identify this point to this point, everything is like this way, I do it. Then I will get what? I will get a cylinder. Okay, I will get a cylinder. That means, look, if this I am taking the space, the product space basically. Easier way is that everything I am doing in Rn, this is R square, the usual distance metric. Okay, so this is going where? Look, this way the identification space. I am just identifying these two sides. Basically, what I'm doing, these two sides, I'm identifying as same side. Basically, so I am getting a cylinder. The cylinder equation will be what? That means I'm going the cylinder. Okay, the base is the circle, unit circle. Okay, so that it will go to this. Okay, this is a quotient space of this. Now from this I can get another quotient space. Now what trick I did here, I do this here. That means I fold. I fold. Okay, so that you will get S1 cross S1. Right? The total. S1 cross S1 it should be. Again this and that. Now you are identifying these two. Okay, so this will be a quotient space of this. You can check that. I could do it on one stage, so it will be a quotient space of this. So the quotient space is transitive. That you should think about it. That quotient map, composition to quotient maps is a quotient map or not. Suppose you have this. Just think about it. Suppose this is a quotient map, this is a quotient, whether this is a quotient map or not. Okay. So this is a quotient space of this. This is a quotient space of this. Actually, this could go straight. This is called Todas. Okay. This up to this much is life is very nice. Okay. Now suppose here, example 9.2. This I'm telling you. T. Make sure that you understand it. But here, this much is fine. Okay. But suppose this, well, this is fine. The next thing, let me go. This suppose. Here, suppose you have a square. Okay. This is not straight line. Don't bother much about it. 2 pi, 2 pi, 0, 2 pi. Here the identification, look what I'm doing here. So it is actually space is this. Identification, I'm going here. I'm sending a point. Okay. So look, x0. That means x0. X0 means somewhere here. So we are identifying with, look what I'm doing. 2 pi minus x, 2 pi. Y coordinate is 2 pi, so it is here on this side. But look how I am identifying 2 pi minus x. That here the problem is that I have taken almost is in the middle. So if I don't take in the middle, let me tell you, then it will be better. Suppose you take x here. Okay, and this is 2 pi. So 2 pi minus x, it is here. So this is, so you are identifying basically this. Okay, you're twisting, not straight. Straight you do, we will get the cylinder. Okay, right? That I'm doing it. 2 pi. Okay. Now what will get? I think you are doing complex analysis. So there is, you will hear the name Mobius transformation. This is a German Mobius strip. Take a piece of paper, square paper, try this. So this is, you are giving a twist actually. Okay, you are giving a twist, and this is generate will Mobius strip. I'm not drawing the picture, you should look, but about Mobius strip, let me tell you something. Okay, make sure that read that. Let me tell you that. Why Mobius strip is famous. Why it is famous. Well, it's coming like a surface. So when how we give the orientation of a surface. Surface and orientation. Look, when I have a line like this, I can go this way or this way. Even if I circle, I can go clockwise or anti-clockwise. So I have orientation. Okay, right? This is a curve, and that in the disk, if you take disk, now suppose it takes disk. This is surface. Okay. Now look, Mobius strip, usually when you have a surface, then how we usually give a direction of a surface. Okay, so that each point of the surface, I think you can read that undergraduate book, Crazy. That, what is that book? Calculus or advanced calculus? I don't know. Crazy. What is that called? Oh, advanced mathematics for engineering, I think. There you will get where he is talking about surface integral. Okay. Crazy, you can do that. I think the pronunciation is wrong. I think pronunciation should be I think so. Look, surface at each point you have to talk about tangent plane. I'm just telling you that briefly on that. But you should read Mobius strip somewhere. You can read in the net also. Tangent plane. So when you give the direction of the surface, to give a direction of the surface, we take the tangent plane at any point, and then you keep moving the tangent plane. Because the reason is, if you move a tangent, if you have tangent plane, then you have the normal. Okay. Usually you have two normals: outward normal, and inward normal. Outward normal means which way out from the surface, or inward normal which is inside the surface. Okay, right? So tangent plane, you have got it, normal. Now look, usually we orient a surface through normal, but like if I want to orient a surface, I always will choose either one of these, either always outward normal or inward normal. That way I do it. Okay, outward normal, inward normal, and whatever you do, that is the orientation. And that means if you start on a surface, now what is orientable surface means? I am not defining, I am just telling you the idea that how orientable surface, you give an orientation. That means actually you give an orientation to the normal. That means suppose at a point you start with your choice, outward or inward, you choose suppose inward normal or outward normal. Suppose you choose that. Then you keep moving over the surface. That means you are also keep moving the normal, and that way you come back to your initial point. Okay, so you keep moving on the surface. That means you are moving your normal. Now suppose you started with an outward normal and then come back to the outward normal again in the initial point. Same normal, not only the normal, in the direction same. Then we call it orientable surface. But if it happens that you can never do that, that you are starting with whether it doesn't matter outward normal or inward normal, when you are coming back, you see that direction of the normal has changed. Direction of the normal has changed. Mobius strip is such a stream. You start at any point with whatever normal you choose, you come back. You'll see that your direction of normal has changed. That means it is not orientable surface. It is not orientable. In differential topology, differential geometry, they basically handle orientable surface. Non-orientable surface is difficult thing to do it. So that's why Mobius strip is famous. Make sure you read on your own something on the Mobius strip. On the Mobius strip, you can read from here. You can read from any book. You can read from Crazy Guy told you. Some nice thing is there. Some short description, but nice is there, and you can read from the net. So that means Mobius strip is not orientable. That's why Mobius strip is famous. Now look, it's a surface, so it is in 3 dimension. I'm just finishing this. It is in 3 dimension. But if you, that I said I twist it from here. Basically, I went to this. Okay. But like the torus, now if I do between these two things, if I twist, then what will I get? You will get what is called Klein 4 bottle. Actually Klein bottle, sorry. What I am suddenly 4 came. I think in algebra you know that you did Klein 4 group. Okay. So this is also Felix Klein. It is in his name, Klein bottle. You will get, if you twist both, then you will get Klein bottle. And that we had at say page 64. This cannot be faithfully represented in 3 dimensions. Basically, it's a 4-dimensional figure. Without this is a 4-dimensional figure, actually. The Klein bottle. So these are all quotient space. So this is actually four-dimensional analog of Mobius tree. Klein bottle is four-dimensional analog of Mobius tree. So you should read that. Here, let me tell you that briefly. I think you know that Klein 4 group, why it is famous. Because I think classification of finite group, that's the big study. Finite groups. I don't know who taught you algebra. Classification of finite groups. It's a big study. You can look at the net. You will hear the name of Thomson. I think who got the field medal. Okay. So here, if you take a group of order 4, the group of order 4, then either G will be Z4 or G will be this. Group of order 4 will be always abelian. This is cyclic. And this is actually Klein 4. That means in a group of order 4, you have only two choices. Either it's cyclic or it is Klein 4. Same Klein. Okay, this is Klein bottle. So my idea is that, my rather instruction is, quotient group, quotient space, you read just to understand all this thing. So what I'm saying, quotient space with this, you read decomposition or identification space. And with this, just have this Mobius strip and Klein bottle. Mobius transformation, that doesn't have any relation with this. You will study in complex analysis. Mobius transformation. Same Mobius, but it doesn't have any relation with that. Mobius was a great mathematician in that sense. So I am just asking you to read these things, the quotient space and that. This is particularly if you are interested later on in differential topology or differential geometry. There is not much difference in the modern differential geometry. Between modern differential geometry and differential topology. When you have basically problems of differential geometry you handle through topology, then it becomes differential topology. Briefly, you can say that loosely. When you handle the problems of differential geometry through topology, that becomes differential topology. Okay, so these are basically the ideas of differential geometry, differential topology. So that I will strongly suggest you just read it. I think you should be interested in that. Okay, Friday I won't take class, so I'll meet you next Monday. Okay, that is okay, next Monday. And today I was checking that I will upload my note on subspaces. Okay, and last night I posted Hort's note on homeomorphism. Make sure that he has some nice examples. So homeomorphism note, you read it carefully. Whatever note I have uploaded, you should read carefully. Okay, and subspace, that's why I'm leaving you 5 days on that. Okay, and make sure many of you are not attending, you are thinking, that's why some of you are clearing for notes, and that you think by looking at the notes, by listening to the recorded lecture, you'll be able to manage it. Topology is little more difficult than your last semester real analysis course. So don't think that, don't treat it like the last semester this. Don't treat topology. Let me write it this. Like MTL 503 real analysis. Okay. Real analysis, still you had some connection with what you have learned in undergraduate. But most of the thing here, we do not have connection with the undergraduate subjects. And that, in fact, here this is, you can say, gateway to advanced mathematics. Okay. So that's why you should take this course a little bit seriously. By doing some advanced mathematics, it's not you only learn that subject. You learn, you mature yourself. You learn some technique, and when you get that maturity, it may help you in other subjects like function analysis also. Function analysis, the problem is that usually students have the problem. Let me tell you, the function analysis, we have the interplay of three subjects. This topology, reanalysis, you can say that reanalysis, and linear algebra. So these three things you need to know well in order to, if you want to understand function analysis well. So these two you have taken last semester. This semester you are taking topology. So you need to understand the basic concept of topology. Okay. Though function analysis, what you will be taught, you only need metric space. Okay. But even then, you need to know metric space and linear algebra very well. But in the US now, they are having something is called topological function analysis. It is function analysis, but you do topological properties. It's called topological function analysis. Okay, that's in. They are trying to identify themselves from the so-called operator theory of that. Okay, operator theory is a different area. It came out of function analysis, but it's not a different area. So that's why in identification problem, they are calling sometimes topological function analysis. Topological function analysis. So make sure that you take this course seriously. It's not that I will say many things with my mouth, which I won't write here. That you can record on that, but you probably won't pay attention to that, what I'm saying. So make sure you attend the class. Okay, I'll meet you on Monday. Okay, next Monday. Okay, bye. ঝামেলা হলো।